Assalamu alaikum and greetings. Here we are in our new video. Our next task is to calculate our magnetic flux density at this point if we have a conductor with this shape with the current I. So we have a current I in this direction, so here will be this, have this direction, here we'll have this, and here we'll have this direction. So, as in previous videos, we can conclude that here we will have first case where we will calculate a magnetic flux density only for this conductor. Then this will be the second case. This is once again half circle. Then this will be the third case, and this will be the fourth case. So we will calculate a magnetic field of every part of a conductor, and our resultant magnetic field, magnetic flux density, will be equal to B1 plus B2 plus B3 plus B4. It is asked to calculate and determine a vector, not only a density but a vector. So we are also given our coordinate systems. We can see which part is x, y, or z axis. How will we calculate this? Using the same old good known rule, Biot-Savart's law, which tells us simplified equation, which tells us that we can calculate a magnetic field, intensity of a magnetic field with this formula. Okay. Now we will firstly analyze our first case, our first conductor. So we have infinitely long conductor, okay, with the current I. We need to calculate our magnetic flux density at this point, so it is a normal to this. So this is our point A, where we need to calculate our magnetic field. Firstly, what will we do? We will determine what is the direction of our magnetic field or magnetic flux density. We will do that all with the same rule of right hand. Okay, we will put them in the direction of the current, and we can see that on this side, the magnetic field, magnetic flux density is towards you, so it has this direction. This is B1, and on this left side, it goes from you to the board. But we need this. So when we calculate, once again, to remind you, Biot-Savart, this formula gives us the way only to calculate a density, not a direction. The direction we will determine visually, like we did now, and we saw it that if this is a conductor, I have circles of magnetic field. At this point, the direction of magnetic field is the tangent, which means if this is a circle, tangent is only towards you. It has only one component, it has this component. We look at our coordinate system and we see that that is the positive coordinate of z-axis. So our magnetic field B1 will have its density B1 times the vector in the direction of z-axis, z-axis. Unit vector for z-axis is k. We will use that. So let's calculate. We have determined that. Let's now, from this point, we need to connect the beginning and the end of the conductor, and we get one angle visually that we can see. So this angle, is it phi1 or phi2? That determines the current. Is this the first angle on which current comes? Yes, it is. This is because this is the direction of the current. This is the first angle, so it means this is phi1. Let's determine right away phi1. What's its value? Once again, we have infinitely long conductor, which means that this angle becomes bigger, and it cannot become more bigger than 19 degrees as our length goes to the infinity, so it is 19 degrees and a half. But don't forget the minus or plus sign. If this current enters at the normal of this angle, this is the normal of this angle, then it is a negative sign, a negative angle. If it comes out, it is a positive angle. Here we have that the current comes in this, so it is a minus phi2. We don't see a second angle. Actually, the second angle would be here, because this is the point. This is the conductor. It gets smaller until it reaches as an angle of phi2 equals 0. And the other thing that we need to determine is this d, which presents the distance of our point from our conductor of this normal. The distance is actually this. And we have that this is a circle, half circle, with the radius a. So in this case, radius is a. So this is a actually. So d equals a, which we have. Okay. In this assignment, we have the value of current and geometry. This is a constant, magnetic constant for air. And you will need to calculate magnetic flux density. But first, very important, before you go to calculate, don't import this. Don't use centimeters. Firstly, all lengths transform into meters. So this is 50 times 10 to the minus 2 meters, or 0.5. Firstly, that's the first step. Please, most mistakes are made because you don't transform these centimeters. You put it in the equations, and then when you need to divide 10 to the power minus 7 or multiply, you lose few zeros. You don't see it, and your result happens to be wrong. So please take care of that. Always firstly transform this into the meters. So now we will put this in the formulation. 4p times 10 to the minus 7 times 2 amps. We know that 4p will be d is actually a, which is 50 times 10 to the power of 2. Sinus phi2 is 0, minus phi1 is minus 90 degrees. Let's once again remember that the sinus of a negative angle is minus sinus of positive angle, so it would be plus sinus of p and a half. This is 1. This and this we can divide. This and this we can divide. So we get that our B1 is equal, let me see, did I calculate it? No. Okay, you can calculate it, but I have been using only, and I will use the expression that we get. It is minus, it actually only this is 1, and we get that it is minus, it is me 0, I for 4pa. if we want to write that as a vector, it only has a k z component, so unit vector k. That's it. Okay, the next case is to determine a magnetic field of this part. So we will draw it. Okay. It is half circle once again. It has radius A, so this is a radius. It has current I. But now what we need to determine is its direction. Once again, using right hand rule. So we will let's imagine that this is a straight line, straight conductor. Use it right hand rule. We can see that this conductor current direction, I have circles, but those circles are going into this way, so at this direction, which means because they are going at this direction, that means that at this point it is a tangent to that circle in this direction. So it goes from you to the board. So this is a magnetic field B2. So our magnetic field B2 has also only one component, which is the z-axis. So it has k, but it has an opposite direction than the positive part of the z-axis. Positive part of the z-axis is towards you, but this vector has here, so its value will be B2 equals B2 in the intensity times minus k. So how will we calculate B2? Once again, we will remember what is the formula for calculating magnetic flux density at the center of circle, and this formula is μ0I over 2R. So this is at the center of the circle, but our B2 is not a complete circle, it's half of circle, so it will be half of this value. So it means it is μ0I for R, where R is a radius, but in our case a radius is A, length A. So we will write it down. So I will rewrite all of these. B1 is equal to μ0I over 4PA times K, and it is Tesla. B2 will be equal, B2 is intensity is μ0I over 4A, but it has minus K. It is an opposite direction from this, our coordinate system, from z-axis. Let's now determine B3. So our third case is this length, and it is very important to draw a geometry. So I have this point A, this is my point A. This begins from the distance of I. So firstly I have distance I, and here is this where it begins my conductor. And here is also, I didn't wrote, this is also the length of I. So this is also I, and this is the end of my conductor. This conductor has current in this way. As we can see it, the current goes this way. And now we need to calculate it. Of course, we are using the same, this Biot-Savart's law. Firstly, in this case, we will use a right-hand rule to determine magnetic flux density direction. So here we have a current this way, we put a thumb and we can see that at this part where we need to calculate the magnetic flux, if this is a current and this is the point, this is the circle, this is the point, at this point it is the tangent, this is the direction, so magnetic flux goes from you to the paper. And I will write that. So magnetic flux density is this B3. So also this magnetic flux has a opposite direction from z axis, so it will have this shape. It's I density times minus k, unit vector of z axis. Now we need to calculate it. I will, because I need to draw my angles, I'll just put it here. Okay. Now, in order to use Biot-Savart's law, we need firstly to draw this distance. This distance, it presents distance of this point from a normal of this conductor. So this is not a distance from here. Why? Because it is not a normal to this conductor. In order to be a normal to this conductor, so we must leave it here. We must draw it this way. So it is a normal here, it is a normal here. It is an angle of 90 degrees. And now when we did that, this is our d distance. So, what are our angles? We can see them. Okay, this is one angle, this is second angle, which will be the first current direction, because the current comes from this, has this direction. This is the first angle, it comes on, so this is phi1, this is the second angle, this is phi2. Now, how can we determine what is value of these angles? Using every geometry that you know, everything that you know from the geometry, we will very easily discover what is this what's this angle. It is again 45 degrees. Why? Because we have here a 90-degree triangle with its cathode. This is first cathode, this is second cathode, and this is the hypotenuse. If we, after we connect this line, so it is a normal to this, we have splitted this angle on two equal parts. Because this is a right 90-degree angle, we split it on the two equal parts. It means that phi1 is 45 degrees and phi2 is also 45 degrees. But very important thing is, once again, the sign, direction of these angles. Are they positive or negative? Once again, we go to the first angle. If the current comes in this normal of the first angle, it is a negative sign, so phi1 is negative sign, and phi2, because the current comes out of its normal, it is a positive sign, so it is like this. Now, what we need also to do is to determine the distance. We don't have a distance. How will we determine the distance? Any way you like. There are so many ways, but I will use a trigonometry. Why? I have this angle. I have hypotenuse. So this is also, I'm looking for 90-degree triangle. I have it here. This is a 90-degree triangle where A is a hypotenuse, D, my distance, is a cathode. So how can I calculate it? By using cosine. Cosine of phi 2 is equal. This side, adjacent side, which is D, divided with the hypotenuse, A. We could also use, okay, if we know this is a 45-degree angle, this is 90-degree angle, we know for every triangle that the sum of all inner angles must be equal to 180 degrees. We can also get that this is 45 degrees. So we could have used for this triangle also that sinus of 45 degrees is equal to opposite side of a triangle. This is D over hypotenuse. We would get the same result. So here we have also our distance. Now we have everything known. We have angles, we have a distance, so we can calculate our magnetic flux density. B3 equals mu0 I over 4P times D, which is square root 2A over 2, which is sine on phi 2 is sine of 45 degrees, which is this, minus sine of a negative angle is minus sine, and this sine will be plus, and it is also this. We have already passed all of this. So V3 equals mu0 I, it has 2PA square root of 2. This is 2 times, so we can also shorten this. So our B3 is mu0 I 2PA. Let me just check. Did I calculate? Okay. This is our density as a vector. B3 is equal V0I 2PA times, also it has an opposite direction as we already discussed, then z-axis, so it is minus K. Unit Tesla for all, please write that down. And the next one, only one case is left. This case is for this conductor. What do we have? We have point A here, and we have the current IE. So this is my point. I need to draw a normal. I cannot draw a normal. I cannot draw this distance, so it is a normal. We don't see any angles, so phi1 is equal 0, phi2 is equal 0. So our B, this is 0, this is 0, 0 times anything is 0. B4 is 0. And now our resultant B is the sum of all these vectors. You didn't have to write all of these vectors. You could just say okay, this has this direction, it will be a positive, this has that direction, it will be a negative, and such line. You can see what will be positive, negative, or you can write it down as vector, which I prefer. Now we simply sum up all of our vectors, and it will be b equals b1 is mu0 I for pa times plus k unit vector. This is minus k, so it will be minus mu0 I over 4a times k. And also this one is minus k, so it will be minus mu0 I over 2a times k. So the end result is b. You put the numbers inside, you calculate it, and you will get around approximately 1.6555 microtesla in the direction of k, in a positive direction of zx. That would be it for this video. Thank you for watching, and see you.